topic today for the next hour is on supervised learning. Actually, I added an additional track there on predictive learning because actually I think that it's a little bit different. What they have in common on supervised learning and predictive learning is that you don't need labels, but I think that the goals in both cases they are slightly different. But you'll see. I hope that in the end of the lecture you understand why I stated unsupervised and predictive learning, while some people consider they are the same. So first of all, there's quite a lot of material from Kevin McGuinness, who's one of these instructors from Dublin City University in Insight Centre in Ireland. You can watch the full video of his lecture 2 years ago here in UPC. So this is going to be the outline for this talk. First, try to motivate why unsupervised learning is important, and then later we go on see what are the most popular architectures, or almost all the most popular architectures, because actually I will not mention on generative models because Santi actually will cover this part later. So I think I found a good link with the last lecture from Oriol Vinyals, where he kind of said, he proposed many problems, challenging problems for artificial intelligence, which were addressed at Google DeepMind using reinforcement learning. And on his talk, he kind of pointed to reinforcement learning as a very valuable path for solving artificial intelligence. And actually, that's what I show here. It's an extract from Slideshot, which is a very popular website where news appear. And at that point, the author of Slideshot kind of said, we know now that we don't need any big new breakthrough to get to true AI. And that he published that just after DeepMind kind of make a good progress with AlphaGo, that system that beat the champion on Go. And then just a few hours later, he got an answer from Jan LeCun. He's one of these famous researchers in the field. He was kind of arguing that he didn't agree actually with that statement, and he said that is completely, utterly, and rigorously wrong. Okay, and he kind of argued his statement saying that most learning that we have as human is actually unsupervised. It means that we don't really have any reward or any supervision at all. And that's why he thinks actually that if you've seen any of his recent talks, he's kind of advocating for that, like that unsupervised learning, that's the topics that we cover in this lecture, is actually the big way to go, where we're going to have more progresses in artificial intelligence currently in the next years. So let's see why he states that. There's this video. Let's see if the audio works.
Evolution has shaped the brain to survive in nature. As to general intelligence, the human brain is the best we know of. Let's look at how generations of scientists have built the brain. A major breakthrough in neuroscience came in 1965, when deep networks were discovered in the brain. The deep networks have since been adopted by scientists. Evolution has shaped the brain to survive in nature. As to general intelligence, the human brain is the best we know of. Let's look at how generations of scientists have built the brain. A major breakthrough in neuroscience came in 1965, when deep networks were discovered in the brain. The deep networks have since been adopted by scientists and also by software engineers to advance, for example, image and speech recognition. But some capabilities of the brain we are just now learning to imitate. Unsupervised learning is one. Artificial deep networks can require millions of man-made examples to work. But the brain learns largely in an autonomous manner, without anyone supplying explicit labels. The field is decades old, but over the past few years, unsupervised learning has been combined with deep networks with great effect. Obviously, those are not the only things the brain
If I do this. Hi. Okay. Fine. Yeah. Okay. I will record it. So that's the introduction from a paper from last conference in NIPS where they did something based on supervised learning. Later, I'm going to comment on this paper, but by now I just wanted to introduce the intro. Good. So let's go back to this famous kick from Jan LeCun. I've mentioned this a couple of times already. Just remember that the unsupervised learning is like the cake itself. So that Jan LeCun considers like reinforcement learning that's the cherry because we really have a few supervisions, a few labels. Supervised learning is where the icing, so based on labels. So based on all the whole amount of data that we're going to process when you work with supervised learning, the amount of labels is very low, and while in supervised learning, it's like the core of the data. That's where we have vast amounts of data. And also notice that he already mentions the unsupervised and predictive learning, which is why I also use this double terminology for this lecture. You've seen this also a few times already in this course. We've covered supervised learning, we've covered reinforcement learning, and now we'll cover unsupervised learning. Just remember that for unsupervised learning, what we want to do actually is not really trying to find pairs of given an input data, try to predict a label, or even given taking many options and trying to maximize the reward at the very end. But now the classic unsupervised learning is like we have lots of data and we want to estimate the data distribution of this data. That's kind of the goal, and then I'll explain you why we want to do that. So now we just want to estimate the data distribution. Why unsupervised learning could be important? First of all, because that's, as Jan LeCun mentioned, that's how human beings or living beings mainly learn from our environment. Because if we can manage to learn without labels, then it will going to be much easy to train agents that will behave like intelligent agents. And because we have also we are nowadays capable of capturing vast amounts of label data, especially in the case of video, where there are ubiquitous cameras everywhere. We have large storage capacities, so there's a lot of data that we can capture and process. About unsupervised learning, let's imagine that you want to build a classifier, and that you take two samples for your problem. Okay, and these are the two samples that you take. So you have only two label samples, a green one and a blue one. And somebody asks you, okay, so given these observations, given this data that you have, where would you put and there are two classes. You want to define a classifier between the two classes. Where would you put this boundary, this classification boundary in this one-dimensional problem? Where would you put it if you only had this information? So the answer is very easy, okay? So I just need you to make sure that you understand the question. So the point is the question. So given two data points, and that's the ones that I show you, this is a one-dimensional problem, one green, one blue, and you only have the information. I want you to tell me what would you do to classify new data that would come later. So if I give you a new sample here, would you think that it's blue or green? How many people for blue? And how many people for green? Okay, many people don't have any idea at all, really. Just using common sense, okay? If the sample would be here, would you label it as green or green people, blue people? Still, some people are not really participating in the okay. So those who are raising your hands, I think you understand the question, and you are, and the answer is quite obvious. Probably, if you only have this data, you will tend to think that the classification boundary is just in the middle. Okay, that would be you would think something like a match merging decision boundary, and that's where you mentally would put that, like based on common sense, if you want, what you have seen so far in life. Okay, but what if instead of just showing you these two labeled samples of the problem, if I show you, okay, excellent. What if I show you this? That now I'm giving you more data. I'm still only giving you 2 label samples, okay? But I'm giving you more data. But the rest of data that I'm giving you is there are no labels there, okay? If now I give you this experiment, and then I'll point here, I guess. How many of you would label, for example, this observation with blue and with green? Okay. And what if I do it extreme here? How many of you would do it with green, with blue? Okay. So even now, yeah, I'm closer to the blue one than the green one, but because of the other samples that nobody has labeled, you are changing your decision, right? So that's one way how you have changed your decision based on data that is not labeled. So you were kind of using unsupervised learning, okay? Actually, in this problem, it's something called semi-supervised learning because I gave you 2 labels, okay? But actually, you modify your decision on some unsupervised learning problem. If I had first just gave you all the samples in gray, you would say, oh, I think that there are like 2 distributions of data here. You would have somehow cluster that, so group them, and you would have taken your decisions based on that. Yeah, so we are always doing unsupervised learning. So that's probably where you would put the boundary in this semi-supervised learning problem. That applies also if you look at 2D data distributions. So again, just imagine you have these 2 points. You only have this information, and you think that okay, now even if that's in this case you don't notice, but it's a 2D problem now. Okay, so remember that earlier there was an axis here, 1D. Now there's no axis. You can think that there are like 2 axes, like x and y. Yeah, but that's because I want to indicate that it's a 2D problem. So if you have no more information, probably you would still, in a 2D problem, on a plane, you would still put the decision boundary in some place, in a location where that it's to the same distance to the 2 samples. But now, what if I show you this data distribution? Right now, again, you have more information than just the labeled samples, and probably that's going to change your decision boundaries, right? Probably you look at the data, you say, oh, now if I had to take the decision, probably I kind of draw this boundary and take my decisions based on that. Yeah. So just notice that in this example, I introduced something new called semi-supervised learning when I use the labels. But if you forget about the labels, about the green and blue color, probably, and I'll tell you, okay, there are 2 classes there, you would still draw the decision boundary in the same place. Yeah. Okay, so actually what we are doing here is estimating the data distribution, the prior of the data, and which is actually something that if you have the information, if we can estimate this data distribution, it can be applied in different classification problems. For example, if you are familiar with the naive Bayesian classifier, you know that this classifier actually takes into account the prior distribution of the data. So this px, or the prior distribution of the data for each of the labels, px, y. Knowing these distributions influences the decisions of the classifiers in this case, and also in the next cases that I will present you. Okay, so that's kind of the interest of trying to estimate the data distributions of your data, of the input data, of the data we are trying to process and classify. So another application for unsupervised learning would be this example here. In this example, it's a 2D problem. You see that samples are labeled between blue and red, and so it's a classification. It could be a classification problem, okay? And just imagine that somebody shows you this data distribution and tells you, hey, I want you to solve this problem with a linear classifier. Okay, so linear classifier, from a graphical perspective, means that you can only draw straight lines. Yeah. Do you think you can solve this problem with a linear classifier right now? No, right? So whatever you try to do, you will have a very bad classifier. So this problem is not linearly separable in a 2D space. And there's an approach that has been explored in many different disciplines and applications, which is okay. So as I see that kind of the data is distributed in clusters. So we can define kind of groups, clusters of data, and there are unsupervised learning algorithms that allow you to do that. Maybe the most famous one is K-means. Maybe you've heard about it. There are several others, okay? But let's imagine that you have some algorithm that allows you to cluster data in groups. Also, here you have the 4 clusters. And now that you have clustered data, what you do is you build a new representation for your data. So in this case, it's something called the back-of-words scheme or representation, where what we do in this case is we just count the amount of data samples in bins. Okay, so let's imagine that maybe you have some. Let's just imagine that these small values here corresponds to 0. Probably it's going to be easier to understand. Okay, and then that you want to represent all the samples in this cluster number 2. Okay, if you do that, then you just count how many samples you have here, and you add them in this counter, in this histogram, and then you would have a vector. Let's again just consider that these are zeros, and then you will have a high value on this bin number 2. And if you want to represent the data which is in cluster number 4, you will have a different representation. Okay, you can think about that as if you code this 0, 1, 2, 3, 4, 5, 6, 7, 0, 7, 0, 0 vector. This is kind of a one-hot encoding, and if you kind of project that in a 4-dimensional space, then that's easily separable with a linear classifier. So actually what we are doing in this trick is we are kind of projecting the data points in a higher dimension space by means of this pre-clustering, and by doing that, now we can separate data easily with a linear classifier. Okay, just think now that the linear classifier is in a 4D space, so I cannot draw it here, but I guess that if you just look at these representations, it's kind of easy to understand how you would classify that, how you could discriminate between the clusters. Here you have, if the example was not clear, here you have a notebook from Kevin where he just ran the example that I just explained. So what he does is he generates some data. He tries to fit a linear classifier on this 2D space, which is a kind of a disaster. And then what he does is he maps it into back-of-words representation. That's when we do this clustering. This BOW means back-of-words. Then he's capable of having the decision boundaries of a classifier that correctly discriminates between the two populations. Yeah. So if you want to see the detail, just click here on the link. So the idea of unsupervised learning is that unsupervised learning mechanisms, they are kind of based on some different assumptions. So basically what you do is you estimate the distribution of your data, and you assume something about how the distribution will behave for unseen samples. So the idea here is that to model the distribution of the input data, we're going to make assumptions, and based on these assumptions, we'll be able to do some inference. That comes from this quote from David McKay that says, "You cannot do inference without making assumptions." So when dealing with unsupervised learning, there are a few typical assumptions that we make. Now I'm going to enunciate them, and later I will give you some examples to better understand what I mean with that. So the first one is the smoothness assumption. It means that if the data points on your distribution, if they are nearby in this space, they are more likely to share the same label. Okay, if you are dealing with a classification problem, that's one of the typical assumptions that you do. And I think that we all of us, when you were trying earlier when you were solving that problem of labeling the points green or blue, and you change your decision based on the whole data distribution, you were kind of applying this smoothness assumption. You kind of assume that as nearby points they will probably share your label, then you kind of move your decision boundary based on this assumption. Another assumption is the cluster assumption, which says that data from discrete clusters, that all data points in the same cluster, they are probably going to share the same label. Okay, and that's kind of related to the other example, the one that I showed with back of words, where there were two classes, there were four clusters, and in that case we tend to think that if there's a cluster of data, all the data points in that cluster will correspond to the same label, and that helps in the classification problem. Another assumption is that the manifold assumption. It says that the data lie approximately on a manifold of much lower dimension than the input space. Okay, so a manifold, it's like a continuous area in the data space. Okay, you can think about like a plane in the data space. It doesn't need to be flat. It could be like a plane, but the manifold is like, let's say, kind of a cluster, let's say. Okay, I'll show you some example of this. About the smoothness assumption, I mentioned already that you have this idea of label propagation. That's how you solve the problem, the 1D problem for classification. For cluster assumption, there are different algorithms. All these are algorithms that cannot relate to this cluster assumption, popular algorithms for unsupervised learning. And for the manifold assumption, for example, very popular algorithms are the PCA. Probably you've seen that in some machine learning course, which kind of assumes that data is it's projected in a linear subspace. And of course, as this assumption is quite strong, that's when deep neural networks come to the help, because you can also assume that the manifolds, they are not linear, that they are nonlinear, and to approximate nonlinear functions, that when deep neural networks are very helpful, and that's where we are going to start now. Yeah. So focus on manifold assumption. This manifold assumption is actually the core idea of how computer vision or neural machine translation or speech recognition is working nowadays. So just to give an example, let's start with the image. Okay, so just consider an image as so just consider each pixel of an image as a component of in a high dimensional space. Okay, so if you have like 20 by 20 image, just consider that defines a space of 400 dimensions. Okay, then if you consider the images like this, and you consider the whole space, and you just go randomly somewhere in the space, okay, probably you will end up in an image like this, something which is absolutely noisy. Okay, where pixels have no relation at all. Yeah. So, but actually, real images, the images that we capture with our cameras, okay, they don't normally have this appearance. Normally have this kind of coherent appearance. Okay, so they are kind of located in a manifold of this super gigantic space of pixels. Yeah, so I explain it again because maybe it's a bit tricky. So again, consider an image, let's say 20 by 20 image pixels, and just consider all the possible images that you can paint with 20 by 20 pixels, which are many. Okay, there are many, but in general, if you just for each of these 20 by 20 pixels, you just take random values, the output probably will have no sense at all. Probably it will be something like this, absolutely completely noisy, something that we will not be able to understand at all. Okay, which kind of means that real images, they are located in a manifold in this 20 by 20, so 400 dimensional space. And assuming that, and having this assumption helps a lot. Yeah, that's kind of the idea. So images, they look like this, they don't look like this, and that helps. So image data, typically, if we did something, we didn't know anything, it would be very high-dimensional data, and the space of images that occur in nature is almost completely empty. So most combinations, they never occur. There are just a few combinations in that space that can actually occur in nature. So the hypothesis that we often base, people who are doing vision or people who are doing language or they are doing text, is that actually not all possible values in this feature space can occur, that everything will be in this manifold. And if we can estimate these manifolds, these data distributions, that will help our task in vision, in speech, or in language. Here, as I mentioned earlier, you would have the idea of the manifold hypothesis. This would be a case of a linear manifold like PCA. So when we do a PCA approximation of our data, we are kind of projecting everything into, in this case, in a linear, in a 1D projection. But if your manifold is not linear, like the ones that we can estimate with deep neural networks, then of course we can have richer data distributions, which might better adjust to our problem. There's another formulation, maybe it's more advanced, but if you want to know more about that, so lately there's these energy-based models that they kind of model these manifolds as some models where when you have observations, you have this, let's say, energy surface, and you want to estimate what's the shape of this energy surface. And what you do is when you have an observation, you push down the energy there. That would be like these blue dots over here. And based on that, you try to estimate the whole shape of the energy, roughly speaking. Okay, so there are ways where popular unsupervised learning algorithms like k-means, PCA, or autoencoders, they can be kind of formulated from this perspective. If you want to know more, just click here and try to learn from this paper and more recent ones. Okay, so that was the high-level abstraction, and I'm going more into architectures about, okay, so all these nice ideas that I presented, how can I implement them? How can I really use them for your projects, okay? And actually, so earlier you were kind of saying that maybe the project you are trying to solve, it's a bit too complicated. So one option you can do is, what I'm going to suggest today, maybe what you can do is take your problem as an unsupervised learning problem, try to see how unsupervised learning can help in your task, even if your task is supervised in the end. I'll tell you some tricks now, and maybe that's a good project for you as well. So here you have the autoencoder. That's probably, maybe you've heard about it, that's probably the most famous and popular architecture for unsupervised learning with neural networks. The idea is that you have some input data, and you have some intermediate layers, hidden layer, and at the output now, what you want to have is exactly the same as in the input. That's why it's called autoencoder. Yeah. So here, if you have this x1, 2, x3, x4, x5, x6, at the output of your neural network, you want is x1, x2, x3, x4, x5, x6. The prediction, and that's it. That's something we can define a loss function based on that, and train a network based on that. Yeah. So maybe you understand why we want to do this, but we can. That's a problem that we can solve. Yeah. So you have your input data. At the output you want to have the same thing that you had at the input. You can define a loss function, maybe mean square error, for example, and train your network with that. And to do that, you don't need any labels. You just need whatever data. If it's an image, it's an image. If it's a song, it's a song. Yeah. Then, of course, the question is like, okay, why would somebody want to do something like that? There are different applications. So, high-level answer what I just presented in the previous slides. Now, more specific answers. So, one of them, and quite popular, is just to reduce the dimension of your data. So maybe you have an image and you want, by some reason, you want to code it in just a few bits or bytes. So one thing you can do is, okay, I'm going to design a neural network where the size of this hidden layer corresponds to the dimension in which I want to code my information. Yeah, and of course, if you just do that, you will probably have losses. Okay, so probably your reconstruction from the hidden layer to the output will not be exactly as the input, but maybe for your problem that's good enough. Okay, that's classic examples: video or audio coding. That could be good enough. Yeah, where losses are acceptable. Yeah, that's the first application, and you can define any size here. It's up to you what size of the network you want to do. So again, going back to the project, that's a very easy project you can do, and you just need input data and just see if you can code it or not. This is the same problem with a different scheme. So you have your data, your encoder, you estimate your parameters for the encoder, your hidden representation, your decoder, you reconstruct, you have your loss function, and with that you just update your weights. Something else you can do, so just imagine that you have lots and lots and lots of data, let's say lots and lots of video, but you only have a few videos labeled. Okay, so one thing you can do is you can take all your whole amount of data, estimate these weights, these parameters for your encoder and decoder network, and then in the end you keep these weights, which will already know something about your data distribution, so they will not be just randomly chosen. And now you can train your classifier on top, softmax or an SVM, whatever. Okay, but at least you will. Well, actually, in this case, the best thing will be a neural network. But in this way, you have already these weights that already know something about your data, and that will make it easier to estimate the parameters that you need for this classifier. Yeah, so you can use unsupervised learning to initialize the parameters for your network, especially when you have the situation where you have lots of data, just a small portion of this data is labeled, but you want to use all the data that is unlabeled. Yeah, so first you do some unsupervised learning, for example, with an autoencoder with all the unlabeled data, and in the end you use the labeled data to tune your classifier. Yeah, so now I'm going to iterate on this idea a few times now, because there are different works have used this paradigm. Here you have a video if you want to watch at home. So one kind of variation of this autoencoder architecture are the restricted Boltzmann machine, which it's kind of an autoencoder, but now the output layer is kind of the input layer again. But it's like we reproject against the input. Now I'll show you exactly the details, but the idea is that it's a shallow two-layer net. Restricted means that no two nodes in a layer share a connection. It's a bipartite graph, and the graph is bidirectional. This means that the weights of these edges, they are shared both when you go from the visible layer to the hidden layer, and where you go from the hidden to the visible, but the biases, they are different. Now I'll show you a more detailed example of this. This is how you train a restricted Boltzmann machine, an RBM. So you may have your just one input data. First we only look at the one input path in a forward path. So with that, we can estimate the parameters, the weights for these edges, and a bias associated to this neuron. Now, if we have multiple inputs, that would be the regular case. We would be able to estimate all the weights of all these edges, all these biases, and whatever activation function. So we have one iteration. And when we have the backward pass, and here that's the characteristic of the restricted Boltzmann machine, is that now the weights, they are the same. I didn't change them, but the biases, they are new. They are specific from the backward pass. Okay, that's kind of the particularity of the RBMs. And normally when you, so the original paper, when you make this, when you back propagate, you use the KL divergent as a loss function, let's say. Yeah, based on that, you can just go forward and backward as many times as you want, and train the weights for this model, for the RPMs. And again, as the size of this hidden layer, you choose it. That could be a good example for choosing for compressing, for choosing the size. And this way, you choose the size of your feature vector. Okay, so you can consider SVM as one type of autoencoder. What happens if we have one RVM after another? Then in that case, what we have is something called deep belief networks. So here it's just a regular feed-forward layer, but you can train it. You can train this network in the following way. First, you just train from the input to the first layer as an RPM. Then from the first layer to the second, but just only this part. Then the third layer, and then just the output. Okay, and that's if you do it this way, that's called the deep belief networks. And typically, again, as I mentioned, you could do all this in an unsupervised fashion, and in the very end, you just train a softmax classifier on top to solve some supervised learning problem. But at least all these weights, they will have been initialized by looking at the data that you are trying to work with. Okay, you don't start just with a few labels that you may have in a supervised learning problem. Okay, so this works. The last two works, restricted Boltzmann machines and deep belief networks. They are contributions from Geoffrey Hinton. He's also one of these fathers of deep learning, currently at Google, but he's one of these big names in the field. Good. So now I just presented the very basic concepts on unsupervised learning. And again, these could be things that you can try with your project if you're really lost. These are nice experiments you can run. And I'm going into more recent works on predictive learning and self-supervised learning. So for these parts, I'm using many material from Junting Pan and Chun-Yu Lin, which are former students of mine. So just remember that Jan LeCun mentioned predictive learning as kind of a variation or subset of unsupervised learning. So what they have in common now is that there are no labels, okay? There are no explicit labels, but you kind of have labels in another way, and I'm going to show you how. The first words that I will just present, mainly I will enumerate them. What they are doing is they are, based on video, they are trying to predict the next video frame. Yeah, and so that's kind of a way of, you don't need labels for that, but you need a sequence of data. Why predicting the next frame can be helpful? Because actually that's kind of, there are many different features in our life, and trying to estimate the different outcomes, actually probably something that we are doing constantly in our intelligence, trying to see, okay, from where I am now, or what should I do to get whatever reward. So having systems that are able to do that might help into solving artificial intelligence. Okay, so that's quite a nice problem to address. And actually, this is a field under research. So if you want to do some research, that's something you can try to do. So there are a few works out there. I'm going to review a few. This one, it's one of the first ones where you have a sequence of input frames, video frames, and the goal is to learn a representation for video. So actually, normally what you do is, so you solve this task that I'm going to present here, but not as a goal. So actually, the goal is not predicting the next frame in general, okay? We can discuss if you are doing video coding, maybe that's what you want to do. But in general, it's not that you want to predict the next frame or you want to predict the future. What you are doing is using this scheme to train a network to learn better, in this case, video representations. Yeah, but that's the goal. And then you will take this feature and you will solve whatever other problem. Okay, again, it's like the unsupervised learning approach. So that's the goal. This scheme actually here, it's like it will solve two different problems. So these are two branches and they represent two different problems. So just note, it talks about frame reconstruction and prediction. So you have a sequence of input frames, and one task we can think about is to reconstruct these very same frames. It's like an autoencoder, yeah, and that's one way in which we can train our network. So you input V1, V2, and V3, and you want to reconstruct V3, V2, and V1. And the other task that we can solve is the video prediction, which is from this representation, you want to predict the next frames. Yeah, video frames. So for input reconstruction, these are results that they obtain. So the one you have in the left, it's one of the frames from the input of the input frames, and the one on the right, it's one of it's 1, 2, 3 frames of a video sequence. So the video sequence here is very simple. It's just 2 and 7 numbers moving around, and this frame is reconstructed as this one as this one, this one, and this one. Yeah. So the idea again is that these 1, 2, 3 reconstructions, all of them come from this single representation that you code it here, you copy it, and just like a kind of a sec-to-sec model, actually, you generate the sequence of video frames. Yeah, that will be for the task of input reconstruction. And then this what it's telling you is that this feature that you have learned, it contains interesting information. If you do the other, I think I didn't update the figures, right? So if you do the other one, would be do the future prediction. What you would generate are the next video frames, and this image should be updated because it's the same one. So we should have different ones here. I'm sorry. So what they saw with this work is that by introducing this scheme, they could learn better features, video features. But then what they took these features and they used them to solve another problem. So actually, these problems here, these are video activity classification. It means that they took this architecture, they learn features from a dataset of video frames, and then with the learned features, they predicted what class of activity was in the video, only based on this learned representation. In this other work, what they were doing is they kind of followed a similar approach, but now they were exploiting the locality of the pixels, also in space, not only in time but also in space. So that was kind of one of advance in the work. Here you have video frame prediction with a ComNet, with a convolutional neural network. So it's a bit more advanced, the model now. Actually, they did something. So this paper is quite famous because what they did is instead of just using one single spatial scale for video frame prediction, they use they first started with a small scale. They predict it, and then they make it larger, and then they did another prediction. So they kind of refine their prediction on a spatial scale. So they use, for this prediction, they use the mean square error. But if you look at the results, mean square error would be like L2 results. So this would be the ground truth. So the input, so the videos I would like to predict, this would be like the one which would be the frames that you predict closer to the ones that you have. So the first ones. But when you go, the more frames you predict, predictions tend to get blurry if you only use the mean square error. Yeah. So mean square error kind of tends to take you to an averaging of all the results. So it's a loss function that you must be very careful with it because it tends to have an average solution. So maybe it doesn't get a realistic solution, but it gives you the average of all the realistic solutions, which is in many cases that's not what you want. So they tried other things like this image gradient difference loss, wherever they define, and something called adversarial training that Santi will talk about in a few minutes.
Actually, next Tuesday.
Sorry?
Actually, next Tuesday.
Oh, sorry. So next Tuesday, Santi will talk about adversarial training. Sorry. So here, there are some of the videos that they predicted. So they have it. Oh, that's a disaster. Here. So. No. Okay, so. Yeah, I think that the ones in red are the ones that are predicted. So they are not super spectacular yet, okay? So, but okay, it's a beginning. Then there's another work from MIT, I think, yeah, from Carl Vondrik, that they kind of improve it a little bit, and they use, again, adversarial training, and they took 3D convolutions for video. So it's just an improvement on that. Yeah, I think you have some examples over here. Yeah, so there are some examples, but there's no audio. So, yeah, so that's what Santi will talk about adversarial training, so you can skip this part. So they have this architecture, and in their work, they try to estimate the foreground and the background and have different predictions. And here, that's what I want to show you. These are the output frames. So you see that, okay, maybe it's a bit weird, the results they obtain, but they kind of look realistic, okay? And the trick that they do is they introduce some discrimination between background and foreground. Yeah, this is another work from MIT. Here the idea is that, okay, so I think these results are not real. So here they're using another approach that Santi will talk about on Tuesday, variation autoencoders.
Not
Today, okay, so Santi will talk about exactly how this works, but they did, so the idea is that they kind of explore this idea that, given one frame, there are different futures that can occur. So they model that with this tool that Santi will talk about soon. And here you have these are 3 different futures that they generated. Okay. As you see, results are still preliminary, but there's an active research line in this field. So in case you want to work on this, one of the nice contributions that they have in this paper is something called cross-convolutional kernels that are pretty good for modeling motion. So if you want to model future frames, model motions, and learn some filters that will predict motions, these kind of kernels, they are pretty good, okay? If that's the case of... Okay, so there's this last part of self-supervised learning, but I'm running out of time, so I should leave it here, and you can check the slides by yourself. Just the basic idea very quickly. The idea here is you see examples using audio and video. So the ones that I showed now, we are trying to learn features by predicting the next frame, because we kind of know that there's a relation between the frames. So they are all of them in the manifold of video frames. If we exploit some things like that, we show to the network frames that they are in the right order or in the wrong order. That's a task that the network can learn. Or you can play with video and audio, so that you can learn audio features that will predict the same labels that an ImageNet model will have on the video frame. So just playing with the alignment between audio and video, that's also a nice way to learn features for both audio and for both video. Again, there's a lot of opportunities here. So I think I'll leave it here. So let's have 5 minutes break, and then Santi will start with the generative models.